I welcome everyone to this new video which explains the chapter Redox reaction from CBSE Class 11. In today's video, we will dive into the world of redox reaction. Chemistry is all about understanding different types of matter and how they transform from one to another. And at the heart of this transformation are reaction. One of the most important types of reaction is called as redox reaction. Redox reactions are essential for many processes that we rely on. They are involved in things like burning fuel for energy, making chemicals, powering batteries, and even the natural corrosion of metals. Today, redox reactions are also tied to major environmental topics like hydrogen fuel as a clean source and the issue of ozone layer. In this video, we will explore what redox reactions are and why they matter. Originally, oxidation referred to addition of oxygen to a substance. Because oxygen is abundant in the atmosphere, many elements react with it, forming oxide. For example, when magnesium reacts with oxygen, it forms magnesium oxide. Similarly, sulfur reacts with oxygen to form sulfur dioxide. These are classical examples of oxidation where oxygen is added to elements. Oxidation was later expanded to include the removal of hydrogen. For instance, when methane reacts with oxygen, it forms carbon dioxide and water, removing hydrogen from methane. Oxidation can also mean combining with electronegative elements other than oxygen. Magnesium, for example, can oxidize by combining with fluorine, chlorine, and sulfur. Oxidation also includes the removal of electropositive elements. For example, potassium can be removed from potassium ferrocyanide in a reaction, changing it to potassium ferricyanide. To sum up, oxidation can mean adding oxygen or an electronegative element or removing hydrogen or an electropositive element. On the other hand, reduction involves removing oxygen or an electronegative element or adding hydrogen or an electropositive element. For instance, in reduction, oxygen is removed from mercuric oxide or hydrogen is added to ethene to form ethane. Since oxidation and reduction occur together, we refer to them collectively as redox reaction. Now, we can explore redox reaction through the lens of electron transfer. For instance, let's consider this reaction. In each case, sodium is oxidized due to interaction with more electronegative element like chlorine, oxygen or sulfur. Conversely, these elements are reduced as they gain electron from sodium. Each reaction can be divided into half reaction which reveals the loss and gain of electrons. For sodium chloride, we can write like this. Adding the half reaction gives us the overall reaction. In contrast, we define oxidation as loss of electron, reduction as gain of electron. Oxidizing agent is the species that accepts electrons, reducing agent is the species that donates electrons. Now, let's examine competitive electron transfer by placing a zinc strip in an aqueous solution of copper nitrate. After some time, we observe that zinc strip is coated with reddish copper and the blue color of solution disappears. Here, zinc loses electron oxidizing to Zn2+, while copper ions are reduced to metallic copper. To confirm the presence of zinc ion, we can pass hydrogen sulfide gas through the colorless solution, resulting in white zinc sulfide when the solution is made alkaline. When we reverse the metals and place a copper strip in zinc sulfate, no reaction occurs, indicating that equilibrium favors the product in the previous reaction. Next, let's observe the reaction of copper with silver nitrate. Copper is oxidized to Cu2+, while silver ions are reduced to form solid silver. When cobalt is placed in nickel sulfate solution, both nickel and cobalt ion are formed at moderate concentration, showing that neither side is favored significantly. From our observation, we can rank metals based on their tendency to release electrons, leading us to metal activity series. Oxidation number is an essential tool in understanding electron transfer in chemical reaction. Oxidation numbers help us track the gain or loss of electron in atoms within a compound. Take for example the reaction of hydrogen and oxygen to form water. Here, hydrogen goes from a neutral state to a positive one and oxygen goes from 0 to a negative state. It's as if electrons partially shift from hydrogen to oxygen. This concept of oxidation number is a bookkeeping method. It helps track electron shift even when they aren't fully transferred, like in covalent bond. Let's look at the rule for assigning oxidation numbers. In a free element, the oxidation number is 0. In a monoatomic ions, oxidation number is equal to ionic charge. Oxygen is usually negative 2 oxidation state except negative 1 in peroxide and positive with fluorine. Hydrogen is positive 1 in most compounds, while in metal hydrates, its oxidation state is negative 1. In neutral compounds, sum of oxidation number will be 0. In polyatomic ions, sum of oxidation number will be ions charge. Fluorine always has negative 1 oxidation state in compounds. Redox reaction fall into 4 main types. First is combination reaction. Here, two substances comes together to form one new substance and one or both reactions must be in their elemental form. Burning carbon to make carbon dioxide is example of combination reaction. Next, decomposition reaction breaks down a compound into 2 or more parts with at least one being an element. Splitting of water into hydrogen and oxygen is an example of it. All decomposition reactions are not redox reaction. For example, decomposition of calcium carbonate is not a redox reaction. Now for displacement reaction. In this, one element replaces another in a compound. Metal displacement is common in extracting pure metals. We can see non-metal reaction when sodium displaces hydrogen in water. Finally, we have disproportionation reaction. Here, same element is both oxidized and reduced. Decomposition of hydrogen peroxide is an example of it. Sometimes we find fractional oxidation numbers like in Fe3O4 where iron has an average oxidation state. But remember, it's not the electrons are in fraction. These averages arise because atoms of the same element are in different oxidation states. Now we can see how to balance redox reaction. There are two methods to balance a redox reaction. First, we can see oxidation number method. Step 1 is to write the correct formulas for all reactants and product. Then assign oxidation numbers to each element to find the atoms that change. Calculate the increase and decrease in oxidation number. If they are in balance, multiply them by suitable factors to make them equal. Add H plus ions or OH minus ions to balance charge and H2O to balance oxygen atom. And finally, check that each side has equal atoms and charges, then it is balanced. Next, in half reduction method, we separate the overall reaction into two parts, one for oxidation and one for reduction. Here also, we need to first write the unbalanced equation in ionic form. In the next step, we need to separate it into two half reactions, one showing oxidation and the other reduction. Next, we have to balance all atoms except hydrogen and oxygen. In the fourth step, add H plus to balance hydrogen atom in acidic solution and water for oxygen atoms. For basic solution, add OH minus ion and then balance charges by adding electrons. Then ensures both half reactions have same number of electrons. Finally, add both half reactions together and cancel out electrons for a balanced equation. Just like acid-base titration that use indicators to find the endpoint, redox titration helps us determine the strength of oxidants and reductants with help of redox sensitive indicators. Our first example is a unique case where the reagent itself acts as an indicator. In a titration involving permanganate, it serves as its own indicator. Permanganate is intensely colored. As permanganate ion reacts with a reductant like iron, the pink color of permanganate disappears. The end point is reached when all the reductants is oxidized and we see a faint pink color due to a very small concentration of permanganate ion. This signals that the oxidants and reductants are equal in terms of their mole stoichiometry. If the reagent doesn't have a distinct color change like permanganate, we can use a redox sensitive indicator. For example, dichromate ion does not change color during the reaction, but by adding diphenylamine as an indicator, we get an intense blue color at the end point. This color change happens just after the last of the reductants is used up, signaling that we have reached the equivalence point. Now let's look at a method that uses iodine as an indicator, ideal for reaction that involve oxidizing iodine ion. When copper 2 plus ion react with iodine ion, it produces iodine. Iodine gives a strong blue color when mixed with starch. So we can clearly see the iodine in solution. To reach the end point, we add thiosulfate ion which react with iodine and cause the blue color to disappear. This color change helps us know when the reaction is complete. The oxidation number concept is a great tool for balancing reaction, but it has its own limitation. Recent understanding shows that oxidation involves a decrease in electron density, while reduction involves an increase in electron density. This electron density approach can sometimes provide a clearer picture of redox reaction, especially for complex systems. We know that when we dip zinc in copper sulfate, zinc loses electrons and becomes ion, while copper ions gain electron to form metallic copper. This releases heat and energy. But what if we could transfer these electrons indirectly? Here's how we can do it. We place zinc in zinc sulfate solution in one beaker and copper sulfate solution in another beaker. Then we connect the beaker with a salt bridge containing a solution of potassium chloride or ammonium nitrate, which allows ion to flow but prevent the solution from mixing. When we connect the zinc and copper rod with a wire and add a switch, we get a complete circuit. Electrons flow from zinc rod to copper rod through the wire, generating an electric current. The salt bridge helps maintain a balance by allowing ion to migrate between the solution, ensuring a continuous flow of electrons and current in this circuit. Each metal has a tendency to gain or lose electron, and it is called as electrode potential. Under standard temperature and pressure, it is called as standard electrode potential. Metals with negative electrode potential are strong reducing agents. I hope you enjoyed this video. Subscribe this channel if you only believe this channel will increase your productivity. Don't forget to share this to your friends so that they can save a lot of time.